All right, we're continuing chapter 2.2 with conditional statements. We're going to talk about Venn diagrams. So in math, we use a Venn diagram to represent the relationships between two different sets. Now, sets, sometimes we can use circles to represent those sets. So this circle here represents one set, and let's just say we have a different set here. We'll just make it blue. And so this kind of looks maybe similar to the Venn diagrams you're used to seeing, where we have one set and another set, and then the overlap that's in between them. So a set can be a collection of things, anything. The word thing here is, I'm saying, intentionally vague because it can be pretty much anything. Our sets are going to be times when our statements are true. So when the hypothesis is true, that's everything that's inside of one of our sets. Or when the conclusion's true, that's going to be one of our other sets. And the way that those two sets overlap each other are going to tell us whether or not we have a true conditional statement or not. Right. Okay, so here's an example of a true conditional statement. If an animal is a cat, then it is a mammal. So you can see here we have our set that represents mammals. So we have a meerkat, I think, a panda, a giraffe, a chimpanzee. Obviously, there's all kinds of things that are mammals that are not pictured here. And inside of that, we even have some cats here, right? Cats are mammals by definition. And so the relationship, our hypothesis is if an animal is a cat. So everything that is a cat, everything that makes that statement true also makes the conclusion true. In fact, another word that we use for this is that cats are a subset. They're a smaller group of the conclusion, which is mammals. So subset is some set terminology that we use here. This is the relationship we need to see anytime there is a true conditional statement. If our conditional statement is true, the hypothesis, right, an animal is a cat, oops, an animal is a cat, the hypothesis needs to be fully contained within the bigger set. If our cat set included some things like this, something that was out here, something that was a cat. So this right here would represent something that is a cat because it's in my new cat set here, but it's not in the mammal. This would be a counterexample. But since we see that does not exist, this is a true conditional statement. All right, so again, since everything that makes this initial hypothesis true falls within the conclusion set, this is a true conditional statement. All right, let's look at a different example here. Sometimes two sets, they have overlap, like here, but they are not representing a true conditional statement. So no matter how we write it, let's just say we have one version of this conditional statement. So if it is Tuesday night dinner, then we will have tacos for dinner. So here's an example of a conditional statement that could be represented by these two sets. We have our set that is our Tuesday night dinners, all the different options we'd have, and then our different times where we have tacos for dinner. There is some overlap, right? We can see in this section here, there's some nice overlap. So at some points we do have tacos for dinner on Tuesday night, but there's lots of counterexamples. There's lots of times where it is Tuesday night dinner, so satisfying our hypothesis, but not satisfying our conclusion, not having tacos. So this would not be a true conditional statement because we have all these counterexamples. And a little set vocabulary here, this section here is called the intersection between these two sets. It's what they have in common. So this would not be a true conditional statement. All right. And here we have another arrangements of two sets. We have this set here, which represents Capulets, a little Romeo and Juliet humor for you, some Capulets and Montagues. And these two sets have no overlap at all. So anything that makes the first set true, anything here that is a Capulet, can't be a Montague because they have nothing in common. And anything over here that is a Montague that makes the second one true would not make the first. So we could make a conditional statement here. So if a person is a Capulet, then the person is a Montague. We even change that color there. Okay, yeah, so this would not be a true conditional statement based on our picture, but this is actually a strange situation where we also are having a hard time, deciding because, well, I guess no, that's not true. For a counterexample, we need a true hypothesis, right? So we need someone who is a Capulet, but then a false conclusion that is not a Montague. So Juliet here is a Capulet, is not a Montague. She would be a counterexample. So this is not a true conditional statement. And yeah, so here's some more set vocabulary here. These two sets are what are called mutually exclusive because they have no intersection. There's no part where they overlap. If you belong to one set, you are excluded from the other one. All right. Let's go ahead and move forward. All right, so for a true conditional statement, we need something like this, where the hypothesis is fully contained within the conclusion. Anytime the hypothesis is true, the conclusion will be true. One easy example to kind of visually see that is with a geography example here. If you live in Illinois, so this is Illinois, then you will live in the USA. So there's no place you could live in Illinois that is not also contained in the USA. So anything that makes the hypothesis true will make the conclusion true, so this is true. A little bit harder, this one here, if x is greater than 3, then x squared is greater than 9. Are there any numbers that are greater than 3 that if I square them, they're greater than 9? This is also a true conditional statement. There is a bit of a place where people get hung up, and it would be maybe something like here. So an example of a number that would fit here would be like, let's just say -4. Because the number -4, if you square that, that is going to be greater than 9. That's going to be 16, which is greater than 9. So this number, it doesn't satisfy the hypothesis, but it does satisfy the conclusion. Is this a counterexample? No. Because it is a false hypothesis and a true conclusion. That's not a counterexample. A counterexample is a true conclusion, something that is a true hypothesis, something that's in the hypothesis set, but not in the conclusion. So this is kind of the opposite of a counterexample. So not a counterexample, but something that people commonly think of when they try to come up with counterexamples. All right. Go ahead and move forward. All right, making a Venn diagram for a conditional statement. So let's go ahead and quickly make a Venn diagram for this. So we know if this is a true conditional statement, it's going to be like this. So we have one set here, and then another one fully within it. So let's put it right there. All right, so if M is the midpoint of a segment, so M is the midpoint. We'll make that a little smaller. So M is the midpoint. That's our hypothesis. Remember, so that's the inside one. Then A, M, and B are collinear. A, M, and B are collinear. Again, I'll make that fit a little better. All right, so I need to think about whether this is true. Is it true that if M is the midpoint of AB, then these have to be in a straight line? Well, seems obvious. Let's draw a picture here. So if you've got a segment AB, and M is the middle, exact middle, they have to be in a straight line. They have to be collinear. If the hypothesis is true, the conclusion has to be true. There's no way. There's no way that M is here, not in a line with them. If it's the midpoint, it's got to be here. All right. So this is a true conditional statement and would fit this set diagram right here. All right, draw an example where the hypothesis is false, but the conclusion is true. Okay, so that means we want M to not be the midpoint, but they are in a straight line. Oh, that's easy, right? It could just be closer to one side. So however we want to draw it, we just want M to not be in the middle, but they are collinear. So A, M, B. It's not the midpoint, so false hypothesis, true conclusion, they are collinear, they're all in a straight line. So M could be anywhere as long as it's not exactly in the middle, that would work. All right, so again, just to really draw this in, the counterexample, that's a really fundamental thing we need to know, because when you're trying to decide if a conditional statement is true, you're trying to decide if there could be a counterexample. So you want something that's true for the hypothesis, but not true for the conclusion. A lot of people will come up with something here where it's true for the conclusion, but false for the hypothesis. This is not a counterexample. You need something in here. Okay. You need something in here that's not in the conclusion set, which based on this diagram is impossible. But if the conditional statement is false, then there exists a counterexample somewhere, and we won't need to come up with it. All right, so let's find a counterexample of these statements here. So if it is spring, then it is March. So we need something that is spring, not March. This needs to be false. This is easy enough. Spring is around April 21st through June 21st, depending on the year. That can switch a little bit, I think. So we need it to be spring, but not March. So any day in April or May. We just need one counterexample. So any day in April would work. Or May, or the beginning of June, or whenever. A lot of counterexamples here, plenty. Next one, if A is greater than B, then B over A is greater than A over B. This one's a really mathy one, so let's just mess around with this. So we need something that's true here. So let's just say 2 is greater than, I don't know, like -3. That's true, right? Well, what happens with these? That means that -3 over 2 is greater than -2 over 3. Is this true? Okay, so this is true, right? 2 is bigger than -3. Remember, greater means to the right on a number line. So if you have 0 here, 2 would be on this side, and -3 would be on this side. So 2 is greater. And then -3 over 2, so that's -1.5. And that's like -0.6 repeating. Okay, actually, this is a counterexample because this is false. -1.5 is not greater than -0.6. It's just not true. So actually, that's a counterexample. So A equals 2, B equals -3. There are probably other counterexamples because we kind of stumbled on that one quickly, but that's one of them. True hypothesis, but false conclusion. All right, let me clear these and keep moving forward. All right, every conditional statement has 3 related conditional statements. So a shortcut way for us to write a conditional statement is this P arrow Q. It means if P, then Q. P and Q obviously are representing 2 statements. So we have the converse, the inverse, the contrapositive. Those are the 3 related conditionals. And we're going to go through what each one is in just a moment. All right, the converse. The converse is formed by switching the hypothesis and the conclusion. So if our original conditional is if P, then Q, the converse would be if Q, then P. Easy enough. Let's go ahead and do this. What is the converse of if you have a sister, then you are cool? So that means if you are cool, then you have a sister. Easy. Right? We took our statements and we switched them. Pretty easy, but I'll kind of underline things here again just to make sure that makes sense. Again, our hypothesis for our original statement was you have a sister. Our conclusion, you are cool. We switched them. So this goes first. If you are cool, then you have a sister. Converse. Inverse. All right. The inverse of a conditional statement is formed by negating both the hypothesis and the conclusion. When we mean negating, we mean writing the logical opposite. So we want our statement to say the opposite thing. So for example, if a statement was, it is Friday, the opposite of that is, it is not Friday. Or if you want to say, it is not raining, well, the opposite of that is, it is raining. Or making it say the opposite. All right, so if our conditional statement is if P then Q, we're going to keep P and Q in the same spots, but we're going to negate them. So we say if not P, then not Q. So what is the inverse of this statement? If you study, then you will do well on the test. Again, we need to negate those. So if you do not study, that's the opposite of that one, right? Then you will not do well on your test. So that would be our inverse. We negated both statements. One really important thing here with all of the related conditional statements is you want to be careful not to change the meaning, changing the words too much, in particular things like verb tense or other things like that, because those subtle changes can make it say something totally different. So be careful with that. Try not to change your verbs and things like that. Just try to make it say the opposite. Usually you can add kind of a negative word like not, won't, haven't, can't, something like that, or take one away. All right, that is the inverse. And then our last one is called the contrapositive, which is actually a combination of those two things. We're going to both switch the order and negate them, and that's going to give us the contrapositive. All right, so if we have a conditional statement, if P then Q, we switch them. Q comes first, then P, and negate. So it'll be if not Q, then not P. That'll be our contrapositive. So if I lose my keys, so I lose my keys, that'll be our P, then I can't drive. So we want to negate these. So I lose my keys. I don't lose my keys. I don't want to say I haven't lost my keys because that's changing lose to lost. That's changing verb tense. So that's a place where people can get in trouble. So let me go ahead and try something out here and see if we like it. So I want to do the opposite of I can't drive. So I can drive. If I can drive, so that's the opposite there, then I didn't lose. Didn't puts past tense in there. So then this is a tough one because I need to add something in there. So then I did not lose my keys. I have a hard time deciding whether that was an appropriate one there. And I won't lose my keys. I didn't lose my keys. Those are subtle. One of them being kind of a future tense, one of them being a past tense. They have subtle different things. Maybe I say I will not. I think I like that the best. Either way, I'm negating it. I'm trying to make it say its opposite. So the opposite of I can't drive, I can drive. The opposite of if I lose my keys, then I will not lose my keys, not lose. So the opposite. All right, and that's our converse. Okay. So quick chart here to sort of help you out. So if you have original conditional statement, if P then Q, the converse will switch those. So if Q then P, the inverse will keep them in the same order as the original, but they'll negate both. So if not P, then not Q. And the contrapositive, kind of a combination of those last two, switch and negate. So if not Q, then not P. This can kind of help you. Some people like it, some people don't. All right, so let's do a quick practice here. Let's come up with the 3 related conditional statements for this. If 2 angles form a linear pair, then the 2 angles are supplementary. Okay, converse first. So we want to switch them. If 2 angles are supplementary, then the two angles form a linear pair. That is our converse. Our inverse, we're going to keep the original order, but we're going to negate them. So if two angles do not form a linear pair, then the two angles are not supplementary. That is our inverse. And the last one, the contrapositive, so we need to do both things. Okay, so if two angles are not supplementary, then the two angles do not form a linear pair. Again, I was tried to be careful not to change any verb tense here and just kind of tried to make them say the opposite or switch them or whatever was called for. So converse, switched, inverse, negated, contrapositive, both negate and switch, or switch and negate. Okay, last practice here. We have these two statements. We're going to decide what relation they have to each other. If today is Saturday, then it is the weekend. If today is not the weekend, then it is not Saturday. Okay, so just looking at it, we'll just call this my P and this my Q, my second. So this one's if P, then Q. So this one is the opposite of Q. So this is not Q. And this is, it's not Saturday. So that's the opposite of P. So that's the not P. So what I did was I switched and negated. So that means that this is the contrapositive. Contrapositive of this statement, because we both switched them and negated them. Now the question is, are these true? If today is Saturday, so if this is true, then it has to be the weekend. So this is a true conditional statement. Everything that makes this true will also make that true. What about the contrapositive? If it's not the weekend, okay, so that could be Monday, Tuesday, Wednesday, Thursday, or Friday. So not the weekend, then it's not Saturday. Yeah, that's also true, right? If it's not the weekend, it has to be one of these days, which is definitely not Saturday. So this would also be a true statement. We're not going to go into this too much, but these two statements, an original conditional statement and its contrapositive, will always have the same truth value. We could get into it, but just enough for us right now to know that that's the case. If one's true, the other will be true. That's not the case for the converse and inverse. Those are independent. They might be true, they might not be. All right, then that's the end of that section.